This 5-microsecond cycle turns 12 volts into 5. The bench model uses one ideal switch, one diode, one inductor, and one capacitor. The switch repeats 2 phases at 200 kHz. Duty cycle is on time divided by 1 complete switching period. For ideal steady-state CCM, 5/12 gives 41.7%. 1 period is 5 microseconds, so on time is 2.08. During on, the switch node jumps to 12 volts. The inductor sees plus 7 volts, so its current ramps upward. Magnetic energy climbs as current rises from 0.669 amps. During freewheel, the switch opens and the diode carries the same current. The switch node falls near zero, making inductor voltage minus 5 volts. Current ramps down, but it cannot jump instantaneously. Equal positive and negative volt-seconds return current to its starting point. That triangular current spans 0.663 amps peak to peak. The load takes the 1 amp average, the capacitor takes the ripple. Positive capacitor current charges it, and negative current discharges it. The ideal capacitive ripple estimate is 8.8 millivolts. Real probes also see ESR, parasitics, spikes, control ripple, and transients. Here current never reaches zero, so this example remains in CCM. The boundary occurs at half the ripple, 0.331 amps. Below that load current, a zero current interval creates discontinuous mode. Then the simple CCM duty relation no longer closes the problem. A synchronous buck replaces the diode with a controlled low-side MOSFET that can reduce conduction loss, but dead time and reverse current matter. Real losses make the required duty wider than 5/12. The simple ledger predicts 44.6% duty and 0.4 watts lost. It still excludes recovery, gate drive, core, ESR, layout, and heat. Read the cycle as routed energy, not as voltage magically disappearing.